commercial seaport is a logistical artery processing billions of dollars in international trade. To secure this massive footprint, port authorities deploy expensive long-range counter-UAS radars, positioning them on the highest crane structures or harbor master towers. To a corporate board, the facility appears completely hardened. But maritime environments obey brutal laws of physics that render standard terrestrial radar architecture virtually useless. A sea surface is not solid ground. It is a massive, constantly shifting electromagnetic mirror. When a radar pulse strikes open water, it experiences severe specular reflection and Bragg scattering, creating an overwhelming phenomenon known as sea clutter. An incoming low-altitude quadcopter or an autonomous unmanned surface vessel does not need complex stealth coatings to breach the perimeter. It simply flies at 15 feet above the waterline, hiding inside the chaotic radar return of the ocean waves. Welcome back to BlackBox UAV. Today, we are breaking down the physical collapse of drone detection in maritime infrastructure, why container yards dismantle radar baselines, and the exact sensor fusion architecture required to secure commercial ports. Even if a radar system overcomes water reflections, it immediately collides with the most hostile RF environment on Earth, the container terminal. A modern port is a dense, ever-changing jungle of corrugated steel. Stacked shipping containers, massive ship-to-shore gantry cranes, and straddle carriers form a complex labyrinth of physical barriers. Radio frequency signals at gigahertz frequencies operate strictly on line of sight. Every single row of stacked steel containers casts a pitch-black radar shadow hundreds of meters long. Worse yet, this environment is dynamic. Standard industrial facilities have static physical geometries. A seaport changes its physical geometry every single hour as thousands of steel containers are moved, stacked, and loaded onto vessels. Static background subtraction algorithms, the fundamental software logic used by security radars to filter out buildings, completely collapse. The software cannot determine if a new radar reflection is an incoming drone or a 20-foot container that was moved 5 minutes ago by a crane. The operator's console becomes a chaotic mess of false targets and dead zones. Faced with detection failures, many port operators default to the ultimate dangerous trap: high-power radio frequency jamming. On a maritime facility, activating an active RF jammer is a regulatory and operational nightmare. Commercial shipping relies entirely on radio spectrum integrity. Active jamming on the 2.4 or 5.8 GHz bands, or blasting broad-spectrum noise, creates severe electromagnetic interference with critical port communications. It disrupts the AIS, the automatic identification system operating on maritime VHF bands, which is legally mandated for international ship navigation. It disrupts S-band and X-band marine navigation radars used by incoming cargo vessels. And most critically, GNSS jamming disables the high-precision GPS systems used by automated rubber-tired gantry cranes and autonomous port trucks moving multi-ton loads through the yard. A single unauthorized active jamming cycle meant to stop a $200 drone can cause a multi-million-dollar collision between a mega-container ship and a commercial pier, or shut down the automated logistics grid of the entire facility. Active jamming in a port is an unacceptable liability. How do you secure a commercial maritime facility without causing operational catastrophe? You must replace broad-spectrum electronic warfare with an integrated, multi-domain physical architecture. First, perimeter detection must move from central towers to the actual waterline. High-frequency Ku-band Micro-Doppler radars should be deployed on low-altitude perimeter piers and sea buoys, looking slightly upward across the water surface to eliminate sea clutter. Second, the radar network must be integrated with dual-band electro-optical and infrared thermal arrays equipped with specialized maritime wave filtering algorithms. These sensors lock onto the physical thermal contrast of the drone's motors against the cold background of the sea. Third, passive acoustic hydrophone arrays and shore-based acoustic sensors capture the unique mechanical frequencies of rotating propellers without emitting a single watt of RF interference. Finally, neutralization must rely strictly on targeted non-disruptive solutions: physical kinetic interceptor drones, automated netting systems, or high-precision cyber takeover protocols that do not flood the maritime spectrum with radio noise. Maritime drone defense is not about buying the loudest jammer. It is an exercise in complex fluid geometry and radio spectrum discipline. An improper CUAS installation at a commercial port does not protect the facility. It simply trades an airborne threat for a massive maritime liability. Stop applying land-based security paradigms to complex ocean environments. Understand the physics of your perimeter. If this technical analysis brought clarity to your maritime security architecture, hit the like button and share this video with port engineers and facility directors. Subscribe to BlackBox UAV for uncompromising defense breakdowns. For direct engineering consultation on maritime threat assessments, site geometry calculations, or custom port security specifications, find my secure contact link in the pinned comment below. We deliver uncompromising engineering truth. Stay secure, and I will see you in the next analysis.